Next, we have a very colorful presenter, Thomas from Flexoptix. He will talk to us about optical transceivers. This is a very interesting presentation. I've seen it already a few times. So there's a lot to learn from it.
Yeah, as Mas already said, my name is Thomas Weible. I am co-founder and CTO at Flexoptix, a company which is specialized in optical transmission and in those tiny pluggable modules which call transceiver, the artificial word for transmit and receive, and you get a transceiver. I brought a topic today where I think is going to be a game changer in optical transmission, and it will change it in a manner which we haven't seen so far. And this presentation today for the next 25 minutes is a little bit about a theory, and then I show a practical example how we implemented it. So, but first of all, where are we currently with the data speed and where we are going towards to? So we do have the 100 gigabit ecosystem, and there are limits when it comes to the tiny pluggables, those modules which you plug into your router or switch. When they were designed, they were never intended for long distance links, so mainly for inner data links, or when they got bigger in size, they can carry longer distances, but then they have a serious issue of power consumption. So as you can see, I mentioned a couple of form factors, CFP, CFP2, and I don't ask you, but I most probably am aware that no one here is using a CFP4 in these days, although it's a 100 gigabit technology, which is pretty fast. So these are all the form factors which are around, and the most known one is the QSFP28. Now, looking at higher speeds with 400 gigabit, the story looks a little bit different. And so far, when we wanted to do long-distance transmissions, we relied on transponder cards. Transponder doing either typically DWDM, dense wavelength division multiplexing. And as you can see, this transponder card is a big card plugged into your optical transport system that you can transport or enlight your dark fiber. On that transponder card, you have a digital signal processor, typically produced in 40 or 28 nanometer structures, and altogether it makes a big card doing one wavelength, for example, 400 gigabit. Now, with the latest developments, which we have seen also in lithography and also in availability of production facilities, the DSP was shrink down to a tiny buck. And this is made either in 5 or 7 nanometer structures now today. And we have the great benefit that those tiny structures need less power, and we can also place it on a pluggable module because we are limited on size. And that's actually what we did. So we took that tiny DSP, and that's the game changer actually. It's massive compute power in an optical module. And it does the conversion. And we place it on a form factor which is the QSFP DD. DD is double density, and that's a great thing. So, but let's start a little bit back in history. Where are we coming from? So first of all, the current transceivers you're using in your network with 1 gig, 10 gig, and even a 40 gig, they are based on a technique, it's called direct detection transceivers. So what you see here, what I show here is on the top left graph, that's actually our rectangle signal coming out of the transmitter. And while it's on the line and getting to our receiver, that's the bottom one, it's not a rectangle shape any longer. It's not a sinus, but it's something between, okay? So all the edges are curved, but the receiver still can distinguish between a 0 and a 1. And typically what we did so far, coming from 1 gig to 10 gig, we just increased the frequency. Pretty simple. So increase the frequency, and for the transmitter it's not an issue, as you can see, but when you look for the receiver, it's getting really serious, because the receiver, he's getting trouble to differentiate between a 0 and a 1. And looking on the right bottom graph now, actually it's only ones at the end of the day, so the receiver can't distinguish any longer. So just increasing the frequency is not an option for higher speeds. And then now coming back to high school, looking into physics, into light, what is light, there are more characteristics and attributes within light, so beside the frequency. And so we used the amplitude so far, but now looking at the phase and polarization, and that's what we're going to do now. So polarization is straightforward. Most probably some of you use the privacy screen on his laptop that the coworker next to you doesn't support your work. That's a polarization filter. Only certain direction of the light are going through that filter, so you can give the light a certain direction. Or when you're wearing sunglasses, we allow only certain polarizations going through your lenses. What we did a simulation now. So in 400 gig, typically we make use of 2 polarization directions. And how would that look like? So that's a typically 16 QAM modulated signal. To the 16 QAM I come later on. That's more on the phase. So what you saw here now is 1 polarization direction simulated, how the signal looked like. We do the second polarization, which is the Y plane as well. Looks like this, just a random message. And now the interesting thing is, when we combine both directions, our signal actually looks like this. So it's a 3D signal, and that's what's detected by the receiver, and also he can distinguish between the X and Y plane, so he separates it again. But the actual signal looks similar like this nice sculpture we show here in this animation. Having said that, at the beginning with the 16 QAM, I need to do a step back. So far, typically when you want to look at an optical signal, and when we are talking about direct detection transceivers, an eye diagram is typically used to measure the quality of your link actually. So an eye diagram, as you can see, you see the curves up and down going. So this yellow lines is our high and low signal, and also the transition from 0 to 1, or even if the signal stays on 1, which is the top line, that's shown here. And the goal is always to have an open eye. So you want to have a defined situation between 0 and 1, and the more open your eyes, the better you can detect this. Now imagine you want to show here phase, and you also want to show polarization. That's not possible. So we need something new. And we introduced the constellation diagram. So how is this constellation diagram built? On the x-axis, we have the real component, and now we make a little bit use of complex numbers, and we have an imaginary part, which is on the y-axis. Looking at a direct detection signal like an on-off keying mechanism, 0, 1, on-off keying, it would look like this. In the middle is our center, and the 0 is in the center, and the 1 is on the right middle plane. All in phase, because we are on the 0 part. As you can see, the quadrature component, we are on the 0 part. We're looking at a 100 gigabit signal, which is typically modulated in PAM4, full level pulse amplitude modulation. We have 4 dots. We have the great thing now, we can modulate 2 bits per symbol, so each square here is a symbol. Which is helpful, so we actually increase the bandwidth just with a new modulation scheme, but it's still in phase. And now, when we add the phase to our signal, it looks like this. So we have 16 dots in total, each dot represented by 4 bits. So that's pretty great. And we have now the real part, but also 90 degrees phase shifted the imaginary part. And that's called 16 quadrature amplitude modulation. And that's actually what we do now in 400 gigabit on 2 polarizations. So with 2 polarization directions and 4 bit per symbol, we can do actually 5 bits in total per symbol, and that's pretty amazing. In real world, it looks like this. So in the real world, some of you might remember this. This is an optical rotary encoder. So how does it work? And I just want to explain the phase shift here. So the optical rotary encoder is the spinning disk, the spinning sliced disk, on a certain time, on a precise time. And we have two photodiodes, the real part, which you see on the left, and then a little bit shifted away with a certain distance, the imaginary photodiode. And the distance they both have to each other, correlated to the defined speed, gives a phase shift of 90 degrees, because what they do is they sample at the same time always, and then your signal looks like this. The great thing about the optical rotary encoder, and that's actually used in printers previously, those needle printers, for example, to look where is my needle head, you can even define the direction the spinning disk with those two photodiodes. Now, you can imagine we don't have a spinning disk in our optical transceiver in there. It's done with electronics. It's a little bit different, but this is more in the analog world how the phase shift is done. Now, a new metric is introduced also with Coherent, or it's not introduced with Coherent, but it's becoming more important now. So the signal-to-noise ratio was always there. But with Coherent technology, you need to be aware of the signal-to-noise ratio. What is it? It's straightforward. When we transmit a signal, a desired signal, we want to have that signal clear. And how is a clear signal disturbed? With noise. So, and the ratio is between the noise level and our desired signal. And yes, even in optical transmission, we have noise level. And people who are doing amplification, they know that you can even amplify noise, and that's not a good thing. So, but that's so far I want to cover about the SNR. Mapping now the SNR to our constellation diagram, it looks like this. So on the left side, you see an SNR of 30 dB. So we measure typically in decibel. It's logarithmic. So 3 dB is double the amount, which is quite helpful for the optical people. And 30 dB is a clearly constellation diagram. Every 16 dots are really easy to identify by the receiver. SNR of 20 dB is getting a little bit blurring, but still doable. And SNR of 5 is actually a big mess. So you can't distinguish to which section the dot belongs to any longer. The receiver can't either. In other words, doing my talk now here in this audience, you're really quiet, that's perfect, thank you for that. That's an SNR of, let's say, 30 dB. So, and if I would do this same talk in a cheering football stadium, then it would be an SNR of 5 dB. No one would understand anything. Yeah. Okay, so far the theory. So now from the practical stuff, what we did. It was straightforward. So we took the pluggable module. That's actually how it looks like. This is this QSF PDD running 400 gigabit with the DSP inside. We went to DKIX because they are around our office as well. We are close to Frankfurt, and they have some latest gear, which also Band showed today. They have a lot of ports, a lot of 40 gig ports as well. So we plugged it in and looked how the operating system of, this is a Nokia box with the SROS running, how do they identify the transceiver, and what matrix do we get out of it? Because we have a little bit more than just the amplitude now. That's what we did. So we run just a single command. So we build a link, a span with 15 kilometers of fiber, and we were running show port and looked how it looks like. And these are 3 sections basically, and I'm gonna go through those 3 sections now. So the first one is more about the physical characteristic of the optical pluggable, and as you can see, it is a 400 gigabit transceiver, and interesting here is the frequency. So beside the fact that we are in the DWDM grid, we can even tune the wavelength of that transceiver. And we see here the min frequency of, I don't read the number now because it's megahertz, it's quite long. We typically do this in terahertz, and this would be 191.3 terahertz. And the max frequency is 196.1 terahertz, or even simpler, just call it channel 13 to channel 61. It's currently tuned to channel 23, and we do support a couple of grids, so we are not tied to a single grid. Typically in 10 gig we were tied to 100 gigahertz and 50 gigahertz DWDM. Now with the coherent ones we can even slice into 25 gigahertz or 75 gigahertz, which is very, very convenient, makes it very flexible. So beside the fact that it is a 400 gigabit transceiver, you also get a fully tunable transceiver just out of the box. The second section is about diagnostic monitoring. The typical 5 values are captured. It is TX and RX levels, it's the bias current, temperature, and the voltage. This is helpful, and now with the coherent plugs, it's becoming even more important that you monitor at least those 5 values precisely, because the temperature is becoming critical. Why? Imagine this tiny plug. It has not a big surface, and all what we do in optical world is we take electricity and we generate heat and a little bit of light. So the light which we are emitting here is 0.001 watt or 1 milliwatt, which is 0 dBm of TX power, which is for the optical transmission quite a lot of TX power. But as you can see, the ratio is all the rest is converted into heat. And you have to get rid of that heat of your switch. Now imagine you have a switch with 1U, 32 ports. Each port is carrying 17 or even 20 watts of heat. When you do the math, you're ending up just on the optical side, just generating 600 or 500 watts of heat. And that's becoming a serious issue. We have seen implementations now that these QSFP-DD ports are sometimes also called a feature called the high power ports. So you can enable this in the operating system, but then your 32 port switch will end up in a 16 port switch because only every second port is used any longer, just to provide enough power for that high power port or those high power ports and get rid of the heat because there are limits. So that's something which is important to know and need to be figured out in the spec sheet of your switch and operating system for sure, if it does support these high power values. Now, coming to the coherent parameters, there are new things introduced now which you don't see on direct detection transceivers. Let's start straight ahead with the tuning part. Typically, when we tune a transceiver, we do this on the TX side. So the RX is typically broadband, we don't care. But now for the coherent one, we also have to tune the receiving side. And why is this important? You can build single fiber transmission with that, or spans. So the TX is, for example, on channel 25, and the RX is on channel 23, and you can transmit on one single fiber then. That's doable. But again, you need to be precise. You need to look in the specs of the transceiver itself. The maturity, they can't change, they can tune the RX side, but not to a different channel than the TX side. And that's just to the fact how the physics are built inside of the transceiver. We need a local oscillator for the base frequency, and that's typically split between the TX and RX, and then we stick to the same channel. Moving on, we have something in optical transmission which is called dispersion. 2 words about dispersion. Dispersion is basically the change of, or the variance between 2 wavelengths while they're traversing on our fiber, so the time difference. So it's more like when people are wearing glasses, you take it off, it's getting blurring, for example. The same is dispersion. While the signal is traveling on our fiber, although we are talking about DWDM, we have a precise wavelength. Although this precise wavelength, again, consists of a couple of wavelengths. And these different wavelengths within this tiny space, they have a different velocity on the fiber. And that's basically called chromatic dispersion. And in the past, we needed to compensate this with components, with dispersion compensators, which are dotted fibers typically. Now with the DSP, this digital signal processor, we have the ability to compensate this with compute power. which is pretty great. So here you can see we have minus 25,000 picoseconds per nanometer, which we can compensate up to plus 2,000 picoseconds, which is a broad range. And even greater is, we can even measure the dispersion now on our span. So we were running here 220 picoseconds per nanometer of dispersion. We did the measurement with the DSP. And when you know the characteristics of your fiber, for example, a G652.D fiber, which is a well-known, laid in the ground since 40 years in a lot of countries around the globe, and this has typically 10 picoseconds per nanometer per kilometer, you can do the reverse mathematics and you can calculate the length of your link. And you would end up in 22 kilometers, which is not true. We had only 15 kilometers and we couldn't figure out where this offset is coming from, because then we used a jumper cable with just 2 meters of cable, and we had a dispersion of 70 picoseconds per nanometer showing up. So there is some inaccuracy in there, but still it's a good metric to figure out how long is my span actually. Beside the chromatic dispersion, and as we are talking now about coherent, we have dual polarization. So we have 2 polarization directions. For sure, between both polarization directions, dispersion can also happen. This is called polarization mode dispersion, and it's measured in the different group delay, and here we have 2 picoseconds. The DSP inside again can compensate it up to 10, 20 picoseconds, depending on the agreement they are following, and then beyond that we can't compensate it any longer. And finally, SNR is also measured, so we have an active measurement device now with that transceiver. This SNR, again, both polarizations need to be measured, and here you can see we were running at 34 dB. It's a perfect, clear signal-to-noise ratio on both polarizations. And then finally, there is a forward error correction. So this DSP has a couple of functions. The major function is to generate the modulated signal, but it also can correct errors when there are errors on our transmission, and that's called the forward error correction. So we add a little bit overhead to our desired signal, and then we can detect the errors while they are on the line or when they are hitting the receiver, and we can even correct them. And the bit error rate before we entered the FEC is here to the power of -3, which is all right, and then the FEC is damn powerful. So we get at the end of the day a bit error rate of 10 to the power of -12 at the end. So we do a lot of correction in there, and it's needed. The RxQ margin is tightly connected to the forward error correction, because that's actually the margin measured in dB, how much margin is left that the forward error correction can meet its specification to the bit error rate of to the power of -12. So when the margin is eaten up to 0 dB, then the FEC is still working, but you will end up with bit errors on the upper layers, so layer 2 and above. And then you will see CRC errors coming up on your interface, and at the end of the day, it's going to be a flapping link, and your link is not stable any longer. Back-to-back link, 2 meter, had roughly 4 dB of RxQ margin. And you might see other implementations, so that's the artificial world from Nokia. They used RxQ margin. The rest of the industry calls it the Q factor. So that's the margin which is still for, leaves some space for the FEC to operate properly. So, now this DSP as well has another side effect which is quite nice. So this is not a single transceiver any longer. So it's not a pure 400 gigabit transceiver with certain power levels. No, it actually can support, as I show here, 15 different application modes. So what does this mean? So this DSP does change the modulation, does change or has the capability to change the baud rate depending on which FEC is used. And then we can do, for example, 2 times 200 gigabit or 4 times 100 gigabit just with that single transceiver. Or if you want to reach longer distances, you you make a more ruggedized modulation, getting down from 16 QAM, for example, to QPSK, which is a little bit more ruggedized for longer links, then you end up with a link doing only 200 gigabit, but all with the same hardware, which is pretty great. I pointed out here the compatibility, and on my almost last slide, I'm going to show the two industry standards which are around. So I pointed here out the OpenZR Plus MSA, and we are currently setting the compatibility to OpenZR Plus MSA. But there are no checks in the operating system because this is the output from the first page about the physical capabilities of that transceiver. We see this transceiver doesn't support OpenZR Plus at all. It's more following the counterpart agreement, which is the OIF. Show it on the next slide. And that's actually what, so we are following, or the transceiver is following OIF, but the configuration on the interface or on the port was set to OpenZR Plus. They don't match with each other. They are running on different speeds and different FECs. So that's really important. You need to know the hardware, what you're having, and you need to know what you're configuring in your operating system or on that port. It won't warn you. Basically, your link won't work if you don't make it correct. Having said that about those two industry, I don't want to call them standards, it's more agreements. There is no official organization behind. These are companies which are tied together and say, okay, we want to make a combined solution. There is the OIF 400ZR, which was a little bit earlier out, and then there is the well-known OpenZR Plus MSA. And they look pretty much the same on the TX and RX power, beside the fact that OpenZR Plus came up with a nice idea and say, hey, we want a high power solution with a high launch power of 0 dBm on the TX side, and that's what they did. They called this the 60HA. I only know what the H means, it's the high. I have no idea about the A, maybe version A. And when you look at the other optical parameters like chromatic dispersion and so on, you see the OpenZR Plus is way more ruggedized when it comes to long distance links. So we have more PMD tolerance, 20 picoseconds instead of 10 picoseconds. We have a way better OSNR, and only 2 dB difference is almost the double, as we are dB talking in logarithmic. So we see definitely a trend to the OpenZR Plus doing there, and that's actually what people are aiming, is the 0 dBm solution, to have a lot of margin on the TX side. And why? Well, you don't need external amplification going through a filter. You can just do it out of the box, running 400 gig coherent on your layer 3 equipment, which is pretty great. So, I said at the beginning, the DSP is a game changer in optical transmission, and I think this graph gives a nice overview why, combined with what I have said in the last 20 minutes. Looking at the green dot, for example, that this is a typical 4-level pulse amplitude modulated signal, which is around for 100 gigabit. Now, if you do this on 4 lanes, you get 400 gigabit. And now, just add a DSP inside who is doing a modulation to the DP dual polarization, 16 quadrature amplitude modulation, you end up at 1.6 terabit. Just due to the fact that there is a chip in there who does a little bit of mathematics. So you quadruple the amount of your link tremendously. That's pretty amazing. Okay. This brings me to the end. We did a couple of tests in different equipment. So as you can see, we did this in Nokia. We already got feedback from our customers doing this in Juniper and Arista. It looks pretty much the same. And there is one important hint. So when you are operating coherent plugs, it's worse. Beside the 5 diagnostic values, which I mentioned on the second section, also add the chromatic dispersion and the group delay. to your monitoring, because then you can also see change of your span and your fiber. That's quite handy. Thank you very much, and I'm definitely open for questions.
I already see Jan in the front here.
Hello, Thomas.
Hello, Jan.
Jan George from 6Connect. Thank you for this presentation. Can you tell us a bit more about the heat dissipation? Because when you increase the speed, you increase the heat that is generated by the module, and you need to dissipate it. Is this a problem in 400G? Will be a problem in 800G, 1.6? How did you approach this problem?
Very good question. Thank you very much, Jan. Yes, the heat is a serious issue. So that we have basically two components in that pluggable which generate heat. First of all, it's the transmitter itself, but the major part relies on the DSP. It's like your CPU or GPU in your computer or in the data center. They generate a lot of heat. And this is always the trade-off and the balance to make the structure smaller, that we can run higher frequencies on the DSP itself and emit less heat. But then, and we need better modulation schemes also for higher speeds, and also finding a nice solution with heat sinks to get rid of the heat. Typically on the pluggables, the challenge is we don't have physical contact when we are plugging it into a switch, so we need the airflow of the fans of the switch, need somehow hit a heat sink, and this heat sink again needs to be attached to the housing of the pluggable, and for sure there is no, you can't put grease or you can't put those thermal pads on it, so it needs to be metal on metal, and that's definitely a challenge, yes. And for sure, the bigger the surface, the better you get rid of the heat.
Okay, thank you. We have another question there.
Okay, thank you very much for the presentation. I saw that you are focusing on the 1500 nanometer range, not the 1300. So solution is mainly for short distances, not long haul distances?
No, this is mainly for long haul distances. So this channel 13 to channel 61 is in the 1550 nanometer area.
Yes. So if it is for the long haul, how you can have the add and drop multiplexers implemented in the data center, or it is by the operator will be implemented?
Well, like you did. So the add drop is independent from the DWDM side. So like you did this with other DWDM solutions. It's the same way you add an add drop multiplexer.
So you need another operator to do the add and drop to the main network in this case, yeah?
When it's not your fiber, yes, you need the operator to do this.
You don't have a solution for that one. It's third party, yeah?
We as a company?
Yes.
No, we are mainly on the transceiver side.
Okay.
And we stick there to the
Thank you
transceiver.
very much.
More than welcome.
Okay, I think we've run out of questions. So thank you very much, Thomas.
Thank you.